Okay, closing up chapter 10, let's talk about buffers. A buffer solution maintains the pH by neutralizing small amounts of the acid or base. So an acid must be present to react any of the OH that's added, and a base must be present to react with any H3O plus that's added. So basically buffers, they make it kind of hard to change the pH dramatically. And so these are great for your body because it keeps that homeostatic level, and I mean, those hydrogen ions, that's what makes the pH scale, right? So if we didn't have a way to bind those and buffer those, then our pH of our blood could tank, etc. So buffers are very, very important. So we get to learn to describe the role of buffers in maintaining the pH of a solution. Okay. So looking at our handy dandy little picture here, when an acid or a base is added to the water, the pH changes drastically because we wanted it to. But again, that buffer solution, the pH is maintained because it's kind of going to absorb those excess hydrogen ions, okay? So the pH doesn't change when an acid or base is added in a buffer solution. So buffers work because they resist changes in pH from the addition of an acid or a base. In the body, they're going to absorb that H3O plus or the OH from foods and cellular processes to maintain that homeostatic pH. They're important in the proper functioning of cells and blood, and they maintain that homeostatic pH level close to 7.4 in the blood. And a change in the pH of the blood, again, is going to affect a lot of things. And one of the main things is it's going to affect the uptake of oxygen in cellular processes. Okay, because remember, hemoglobin is actually it's very much regulated by the concentration of hydrogen ions. That's actually called the Bohr effect. Okay, look it up. It's kind of cool. So components of a buffer. A buffer solution contains a combined acid-base conjugate pairs, a weak acid and a salt of its conjugate base, such as a weak acid and the salt of a conjugate base. And it has equal concentrations of the weak acid and its salt. So they work because, for instance, in the buffer with acetic acid and sodium acetate, the salt produces acetate ions, okay, and sodium ions. Then the salt is added to provide a higher concentration of the conjugate base than from the weak base alone. And so this is a large amount and a large amount, and then the other ones are the smaller amounts. So again, the function is of a weak acid in the buffer is to neutralize the base. The acetate ion produced in the neutralization reaction adds to the concentration of the acetate already in the solution from the salt. So again, you can see here, you have your acetic acid and your base, and then you have your acetate ion and the water. So the functions of the acetate ion, which is the C2H3O2, is to neutralize the H3O plus from the acids. And the acetic acid that's produced contributes to the available weak acid. Okay. Buffers work because the weak acids in a buffer neutralizes the bases, and the conjugate base in the buffer neutralizes the acid. So the buffer described here consists of equal concentrations of the acetic acid and its conjugate base, which is the acetate ion. So adding H3O plus to the buffer is going to react with that C2H3O2, whereas adding the OH neutralizes the C2H3O2. The pH of the solution is maintained as long as the added amounts of acid or bases are small compared to the concentrations of their buffer components. So let's try to apply this. So which of the following combinations make a good buffer solution? So pause me and come back. All right, so remember that a buffer consists of a weak acid and a salt of its conjugate base. So answer A, HCl and KCl, is not a buffer. B is a buffer with a weak acid and its salt. C is not a buffer, okay, where D is a buffer because it has its weak acid and its salt. So here is your concept map about everything that we talked about today in chapter 10. So I hope you guys are having a fantastic day, and we'll see you in class. Thanks.